made a wrong condition on this E1 mechanism because this one, sodium OCH3, that's actually a small strong base. Small strong base, and that condition is not going to happen E1. So please change that into alcohol, change that into methanol. Everything is the same, apart from you cannot do O- directly. You have to use the lone pair on oxygen to form something positive, because E1 and SO1 usually happens in a acidic condition, which means you should not have O- or strong base around you. Make sense? So today we are still going to do the NMR first, and I'll try to finish that soon. And then after that, we're going to review substitution and elimination. Last week, we only talked about which hydrogen is going to have the same peak. We didn't really talk about what happens if you have neighbors, which means what the neighbor hydrogen has influences on you. So we only care about if you have electron withdrawing neighbors, but how about the hydrogens? So this week, we're going to learn N+1 rule. On your discussion menu, I think it's kind of, it takes you some time to see that neighbor, but basically the neighbor I'm talking about this week is the neighbor hydrogen that's bonded to the carbon next to you. So I'll say that again, it's the hydrogen. It's the hydrogen bonded to the carbon next to you. On your discussion menu, so you can see this. So for this HA, HB is the neighbor. So it's not the hydrogen bonded to you, it's the hydrogen bonded to the carbon next to you. This one is also going to generate a really small magnet, and that's going to shift you. So it's going to be spin up or spin down. So spin up is going to make you left, and spin down is going to make you a little bit right. That actually separates your peak into two. So last week we only learned, okay, if I have nothing else, my hydrogen is going to be here. This week, what you should take from this N+1 rule is how many neighbors you have is going to separate peak into N+1 peak. So that's, you will see by practice, so like this. When you don't have neighbors, your peak is your peak itself. It's a singlet. When you have one neighbor, because your neighbor is going to be spin up and spin down, so finally you are going to be separate into two peaks, and the average of that two peaks should be your original singlet. Does that make sense? And if you have two neighbors, that's 1, 2, 1, 1, 2, 2, 2, 2, 1. You are going to have a triplet because your neighbors, that's kind of handy to use. So your final peak is decided on your neighbor hydrogen. The number of your neighbor hydrogen, if you have 3 neighbors, that's going to be 4. On your discussion menu, so it's something similar to this week that we're going to ask you what peaks it is, how many peaks it's going to be affected by your neighbor hydrogen. So for your quiz next week, you should practice on this. But I don't think it's clear if I just told you that. So I do that on the back of my week 7. This is an example that is not, it is kind of quite plain because there are only 2 peaks for this hydrogen. It's on benzene ring, so it's within 6 to 7. Actually, this is also going to be a peak somewhere around 2, or no, maybe 3, but we are not going to discuss that one yet because for these 2 hydrogen, they only have this one has a neighbor carbon, and that carbon only have 1 hydrogen. So originally, this blue one is here, and this red one is here, originally. But because this red one is going to have spin up and spin down, so it's going to make the blue shift a little bit higher and spin down. So finally, the peaks look like this. The same thing for the blue one, because the red peak is going to have spin up and spin down. So it's going to affect that one into this 2. So on the back of your page, this is the real spectrum that I use a special software to predict. So actually, actually these two hydrogen looks like this. So that's what I mean by here. It actually has two peaks, and the center of the two peaks is the real number that's if it doesn't have any hydrogen. Does that make sense? So now on the back of the page, I choose the samples which only give you two hydrogen peaks, which means now we are starting to practice on how to interpret the peaks. Remember from last week, I told you guys, your ultimate goal for this part is finally you're going to solve the NMR problem by your own, which means you should know each peak corresponds to which hydrogen on a complex molecule. So this time it's a simple version, only two hydrogen peaks. Let's figure out together. So like this one. So after you learned last week chemical equivalence, this hydrogen has a peak, and then this one is chemical. These two hydrogens are chemical equivalent to each other, right? How many neighbors does it have for the blue one? It has only one red hydrogen, so neighbor is one, right? So one neighbor, I personally like to use this method. It's a CH2 and it has one neighbor. The same thing for the red one. It's a CH with two neighbors. That's just my own habit, and you will see the benefits of this one when you really come to solve problems on that. So just build up this habit now, and I'll explain later. Maybe next week. Okay, so according to our n+1 rule, this one has two neighbors. n+1 equals to 2 plus 1 equals to 3. And this one, it has only one neighbor. n+1 equals to 1 plus 1 equals to 2. So I'm expecting to see 3 peaks for this hydrogen, and I'm expecting to see 2 peaks for this hydrogen, for these two hydrogen. Does that make sense? And let's see what's on the peaks. So on the peaks, this one is a triplet, 3 peaks. So it's a 3 peaks, and this one is a 2 peaks. It's doublet. So 3 peaks. We sometimes use TR for triplets. This one is 2 peaks. We use doublet for 2 peaks. So let's match them. The one with 2 peaks should be this. The one with 3 peaks should be this. So this is kind of a simple interpretation of this spectrum. So this compound only have 2 sets of peaks, and I know which one corresponds to which. That's kind of your getting your hands on solving problems for interpretation now. Does that make sense? Yeah, question.
Would the amount of hydrogen then make them taller?
Yeah, that's the second hint. It's like this one is 2 hydrogen, so the intensity, this one is 2, so that one is 2. So I labeled the 2 here. That's another hint that you can use. Okay, this one. So these 3 are the same, and they have 2 neighbors. So it's 2 neighbor CH3. This one is 3 neighbor CH2. So this one should have 3 plus 1 equals 4 peaks. This one should have 2 plus 1 equals 3 peaks. So this is a triplet, and that one is quartet. Let's see. Quartet and triplet. So the triplet should be this one, and the quartet should be this one. Also the intensity, 2 and 3. Okay, by looking at this example, can you figure out the last one by your own? This one, why it has 3 neighbors? Because this is the carbon number 1, this is the carbon number 2, so that's your neighbor carbon, and on your neighbor carbon you have 3 hydrogens. That's what I mean by neighbors. For the last one, those two methyl groups are in chemical equivalence, so those 6 hydrogen have the same peaks. It's kind of last week discussion because you have a symmetrical plane here. So these two methyl groups have the same hydrogen. These 6 hydrogen are the same. So it's 2 methyl group CH3 multiplied by 2. And how many neighbors does it have? Only 1. So this one is a 1 neighbor, CH3. According to n plus 1 rule, is 1 plus 1 equals to 2. How about the red hydrogen? This one, it has 6 neighbors. So it's a CH with 6 neighbors. So n plus 1 equals to 6 plus 1 equals to 7. So this one, 7 peak. This one, 2 peak. Also the intensity told you that, 6 hydrogen and 1 hydrogen. So this is kind of the easy interpretation of which peak corresponds to which set of hydrogen. And in your future, you are going to learn something more complicated, and this is kind of the basic skills that you are get on to interpret NMR spec. Okay, so practice on the discussion manual one. Okay, last week we end up with the table. So can you write the what type of reaction that you're going to have on the table, because we talked about that last time, and I want to force you guys to practice on this. We're going to check the answer together. So I give you 2 minutes to write the table because it's handy to use and you do need to use that. Don't check the notes, just try to see how much you can memorize. Check how much you get the things correct. Your midterm is next Tuesday. So I hope you use these 2 minutes to make you feel painful on this table, and you do remember that. You remember the place that you get wrong, so you are not going to forget it when next Tuesday. On my second midterm in my 118A, the first thing after they say start, I draw the table here. So let me see how much I can remember. 1, 2, 3, 4. You can draw with me, although you just did one. But this is more handy to use. So weak nucleophile, good nucleophile, strong base, and a bulky base. Methyl, primary on branch, primary branch, secondary, and tertiary. Secondary has a box separated here. I'll zoom in so you can see clearly. Here, see, use table. Okay, no reaction for the first 3. SN2 here, SN2 here, SN1 here, E2 for the rest. Oh, SN2 here, E2 here, E2 here, E2 for the down, E2 for the down. That's down. And then whenever you have SN1, you always have E1. So I just don't have enough space to write here. How many seconds did I take? You should be able to do that on your next Tuesday exam, okay? It's not hard. Let's see how this table works. First one, try to do it on your own. If you feel pain, that's good, because this is what you're going to look in your second midterm. If it's not me, you're going to feel painful in your second midterm, okay? So I force you guys to practice during the weekend. If you feel embarrassed, I know nothing about that, go practice. So I would rather you hate me now rather than hate me after the second midterm. My TA teach nothing. You can walk in pairs if you want. I'll give you a few, maybe 5 minutes to work on the front page and I'll walk through them, okay? 3 steps in doing table question. So I will call this table question. So if it's a table question, a good living group, and I usually just put a kick here that I know it's a good living group. Second thing, you check if this center carbon, which is the carbon that your living group is bonded to, your center carbon, what carbon it is. So this one is 1, 2, 3. It's a tertiary carbon. And the third thing is you check, is this a nucleophile or base? So CH3OH, tell me it's a nucleophile. A vote for nucleophile, hands up. Vote for base, hands up. How about the rest? Okay, CH3OH is alcohol, ROH. R means, R at your stage means CNHM. So CH3OH is alcohol. So alcohol is a weak nucleophile. Can you tell me what reaction it is? Good. So identify what SN1 is. It's just the first step, and you're gaining 0 points for this because you need to write the correct product. See what the question is. Usually what you need to do is write the major organic products, or read the question, write all the products, and identify which one is major. Those are two different questions. If it asks you to write the major organic products, then you just need to write down which one is major. But I guess what you are going to miss on your second midterm is write all products, identify which one is major. So I will treat this worksheet like this. So all the products means even you have some byproducts, you need to write them on as well. But anyways, SN1. So I will just write the product directly. I will use a different color so you can tell which one is how you think, which one is the answer. Okay. So this is the correct answer for this one because it's SN1. And on the mechanism of my note 6, you should be able to know it's going to leave the living group leave first. Oh, this is not the answer part. This is just analysis. So I go through. So this is only the green part is the ones you should write on your exam. The rest of them, I use pencil for how I think. I use orange for mechanism. So this one leave first, and it's going to generate this one. So it's a carbocation center, and this one can attach from top or from bottom. So you're going to generate racemic mixture.
Oh, I have a question.
Yeah.
So what happens? I drew what you drew, but instead of drawing the stereochemistry, I just did
Plus, minus.
No, I didn't draw any stereochemistry because I thought it would be assumed that it's
No,
more
you
natural.
have to.
You have to draw the stereochemistry.
Yeah. So that's a good question. You have to show your stereocenter. Otherwise, you're going to lose point for that part. Okay? Next one. So, OTOS is a good living group. At your stage, you just need to know that. Yeah, question? Oh, let me, so, okay, I'll let you ask first. Yeah.
Is plus or minus okay?
Yeah, plus minus okay. Your question, yeah.
We leave out what happens with the bromic acid. We leave that out, or are we supposed to write that down as well? The HBr.
HBr.
Yeah.
Yeah, you can write that thing down, but this one is not organic compound. So it's usually ask you to write the organic products. So if you are, in the example later, that if you are sensitive something with alcohol, you do need to write that alcohol because alcohol is an organic product. HBr is just a gas, but if I were you, I would still write that things on. So it doesn't hurt you. But yeah. Okay.
So we really expect that we would put another product like the HBr.
Yeah. If I were you, I would put everything on. Okay. Yeah. Question?
Do we have to show the orange too? What you wrote in orange?
No.
No.
So green part is the only place that your answers should look like. So later on, you can check my answer key. I differentiate the color. So orange part is for analysis, mechanism. Pencil is for how I think. Good. Okay, next one. OTS is a good living group. At your stage, you just need to know this. I will, if I have time, I'll go over what this is, but I guarantee you don't really want to know the structure. KOH, what's that? Vote for nuclei, hands up. Vote for base, hands up. Okay, it says small, strong base. Where it is? Because KOH equals to K plus at OH minus, and OH minus is here. Small, strong base. And then this one, good living group, what carbon it is? 1, 2 is secondary carbon. Acetone is a polar aprotic solvent. Okay. For the solvent part, it's also on my note 6. It's here. That's the solvent part. Just let you know. So, what reaction is going to be? This one. Look at the table. Shout out. E2. Good. So for E2, did you remember what I talked about last time? You need to pay attention to what? Anti-hydrogen. So it has your leaving group and the hydrogen you're going to eliminate. So there are 2 hydrogen here. One is wedge, one is dash. You have to eliminate the anti-position hydrogen, which means in this case it doesn't make any difference, but it will in the future. So you should eliminate this one. So the answer looks like this, although it doesn't make difference here. Okay? But how it works is your OH is grab this hydrogen and then kicking the leaving group off. So you also have OTOS minus around, but you don't have to show that. Okay, next one. Do you want to practice a few on your own, or you want me to go through the, question? Yeah.
I was just wondering, can you go over again how you know that's a secondary?
This one?
Yeah.
So, do you want me to go through mechanism or through what?
I was just wondering why that's supposed to do that.
Okay, so it comes from this, the EQ mechanism. This one is the one that I asked you guys to make on a flashcard. So last time I talked about this, and what I did last time is I highlight this one. So this has to be anti-position. This is what, do you still remember? So in week 2, we talk about the Fisher projection. So if you really look at this one, so good things I have the bond with me. Okay, if you know this part already, go ahead to do the questions. And yeah, so I will go through them. This one, so this is what it looks like. So I want you to eliminate this hydrogen, but usually your bond doesn't, it's not always the case that you have your anti-position. This is your leaving group. Okay, this is your leaving group, and there are several hydrogen. So what each you do is you rotate until your hydrogen that you want to eliminate is in anti-position. So here is anti-position to your leaving group. And then base grab that hydrogen, form a bond here, kick the leaving group out. So that's what do I mean by anti-position. So on this one, if you cannot see that anti, it's because one is dashed into it. So your leaving group is dashed in, and your hydrogen is wedged out. So I want you to eliminate this wedged out hydrogen. So base grab this hydrogen, form this, and then kick the leaving group out. Make sense? Yeah, question?
So what happens if the leaving group was on a wedge? Would you want to eliminate the
Dash
hydrogen
one.
that's on the dash? Okay.
Yes. So if the leaving group is on wedge, I want you to eliminate the dash hydrogen, which is here. Okay? Let's move on. So it's the same. If you want to hear how I solve the problem, you can hear. Otherwise, just move on to the front page and finish them. Okay, so chloro is a good leaving group. I checked here, and this center carbon is 1, 2, so it's a secondary carbon. NASH. Vote for nucleophile. Good. Vote for base. Good. So it's a nucleophile. It's on the table. I think it's pretty. Where's my table? Okay, it's pretty obvious. It's this one. So whenever you see sodium or calcium, you can always write them into sodium plus SH minus. So this is your nucleophile. SH minus. And then it's a good nucleophile. This one is not alcohol. This one is polar aprotic solvent. It's not alcohol. So your solvents, if I didn't list them in, if it's not water, not acid, not alcohol, at your stage you can think about that's going to be polar. So polar aprotic solvent. So that's what you should think. So same thing for DMSO. DMSO is also a polar aprotic. DMF is also a polar aprotic. So I would do this. If it's not water, not acid, not alcohol, it's going to be. So this one is alcohol. So this is polar aprotic. For solvent part, did I make this one clear? Question?
I think it's a good idea to memorize the list of the nucleophiles and the bases.
You have to if you cannot compare by your own. It's like what usually students do is they can differentiate, go through what I told you last time, this. So that's why I put nucleophile and base here. So you should be able to compare, is this a good nucleophile or is a good base? But I assume you don't have that skill yet. So if you can memorize a few examples, it would be really handy. But with the time moving on in your 1 ATP, I think that's the time that finally you get like a sense if there's a good nucleophile or not. But currently, you should have that skill, but I don't think it's that fast. Okay?
I think short one says to understand the force.
Yeah, so he used that tools. I go to see the video. He did bring that Fufi tools. What he wants you guys to understanding everything, how that polarity works and why this. But for your case, I would say make your life easier. Is just remember a few examples. Yeah, question?
So what would N3 minus be? I don't really see it on the table.
N3 minus.
Yeah, would that be a nucleophile, a base?
N3 minus.
Because I've seen that in problems.
I think it's with something else. I can talk to you later. It's not N3 minus itself. It's something else.
Okay.
Yeah. Okay. Where did I stop? Oh, here. So this is a good nucleophile, and then its secondary is polar aprotic on my table. Secondary polar aprotic is here. Good nucleophile. It's SN2. So you're only to have one product. Oh, the green pen. Okay. It's going to look like this. Okay. This one. It's a ether. So CH3O CH3. This is what it is. I told you CNHM is R. So this one is R O R. On your table, where is ROR? It's a weak nucleophile. So ROR, and do I have a good leaving group? I do. What's my carbon is primary and it doesn't have branch. So primary unbranched. Weak nucleophile, primary unbranched, no reaction. Oh, the green part, no reaction. Questions so far? Okay, I'll leave the rest two to you guys, and then give you 1 minute to do this too, and see how far you are going. I'll zoom out for the whole page so you can see how I learn, how I think. So Is OH a good leaving group or not? Vote for good, hands up. Vote for not good leaving group, hands up. Great, so you stop here. Because it's not a good leaving group, you don't use the table. But this is still a reaction you learn before your first midterm. It's the acid-based one. Okay, it's really tricky, but that's true. So what happens is this. You have an oxygen, you have a hydrogen. And NH2 is a strong base. Looks like this. So this is still how you think. Does that make sense? So finally what you have, your answer should look like this. O minus. NH2. Or NH3 is fine. Make sense? It's really tricky, and I see a lot of students just do it directly. This one and this one are tricky, but I do want you to pay attention on that. Okay. Last one. This is a good leaving group. And then this one is a small strong base. So I heard the question, how do I know it's a small? Bulky base, at your stage, you only learn these two. One is O third butyl, so which looks like this. So O minus. The other is LDA, which looks like this. I think in your stage, you only learn these two bulky base. So if it's not one of these two, it's a small strong base. Question?
Yeah, for F,
F?
for F, I thought that would be no reaction since it's a bad leaving group.
Yeah, it's bad leaving group, but you still have acid-base reaction. So it's not the table question. For table question, it's no reaction. But we didn't say you only write the product for table question. It's acid-base reaction. Yes? And then think about a question. For your second midterm, you only learn halogenation, acid-base, and table questions. For your final, you learn something new. And you need to identify if this question is a table question or not. Does that sound really scared?
Yes.
Okay, so your midterm should be easy than your final. Think about that. Sounds more comfortable.
Why would we think about that right now? Why would you make us think?
Just make you feel better for your second midterm. You learn that, and we didn't say only write table question, right? Yeah. So you are responsible for write product for reaction. We didn't say only write product for reaction of table question.
But then it's not on the page the rest of 1 and 2.
No, we won't.
I'm saying.
Yeah, this. Okay. Back to the last one. Let's finish this page. Come on. Okay, OTS. This is a good leaving group. If you see something with O, actually on the handouts I just passed around, there's a list of good leaving group. So that's why I say I guarantee you don't want to know the structure. Where's my extra? I forgot. But it's on your page. It's on the page of that. So there's an example. So you just need to know. Usually they have O something. So O something, it's usually a good leaving group. So that's how I remember when I was in YIT. Okay. So good leaving group and small strong base and polar protic solvents. And this carbon, center carbon is 1, 2. So that's secondary, small strong base. Okay, so that's E2 already. E2. So this one has a dash hydrogen. This one has a wedge hydrogen. Which side do I go for HA or HB? Vote for HA. Vote for HB. Good, because HB is dash. Our leaving group is wedge. I just told you, you need an anti-position hydrogen. You have to eliminate the anti-position hydrogen. So you have to eliminate HB. So your final product looks like this. I change the question a little bit. If I use a blue pen, so it's the same thing, but I put a methyl group here. So this one is a methyl group. Everything is the same. Maybe bromo. So bromo is also a group leaving group, and a dash. The same condition. The blue one is going to be no reaction because you don't have that anti-hydrogen. Think about this question. Because you don't have that anti-hydrogen, so if it's blue one, I block here, it's going to be no reaction. Okay, so if I ask the third question, it's really quick, but think about this. If it's not this, I don't have this side of the ring. So it's this, bromo, dash, wedge, what's going to be? If I don't have this side of the ring, then the reason I cannot do free rotate is because of the ring. The ring limits, so the ring looks like this. You cannot rotate the hydrogen, the carbon-carbon bond, but if you don't have the ring, see, that's why I need this model. Then you can do whatever rotation you want. Does that make sense? So if I don't have the ring, I just like this. You can still do elimination on this one. So there's a wedge hydrogen, but if you rotate it, you can still do elimination on that one. Does that make sense? So it's really tricky for this one. Go back to rewatch this part if you cannot understand now, but it's kind of, I can told you it's the same question, but I can make many questions out of it. Okay. You have a question?
So when you brought that third question, so where would the elimination happen then? Because
There's only one hydrogen.
right.
This one doesn't have, oh, there's another hydrogen, right? Here's another hydrogen. If I didn't say there's a carbon, there's another hydrogen. Did you learn Hoffman and Zaitsev already? Hoffman product, did he brought this one in? So like, you're going to generate more substituted alkene. Did he say that or not? No?
No.
No, then you don't need to worry about which side yet.
Oh, okay, so if you had like two hydrogens on the dash, you're not gonna see that?
Why do you have two hydrogen on a dash?
Well, no, like I was just thinking, like, I was making my own question up.
Yeah. So if you have, usually it's going to be two solid line, one wedge and one dash.
So what happens if like you have the two hydrogens on dashes, like one hydrogen on a dash here, one hydrogen on a dash here? Where would elimination happen?
Okay, so this is the square that I didn't cover last time. So it depends on, I will go through that. So even he hit exam on this, you still get. So when that happens, it depends on your base. So LDA is a bulky base. I will zoom in a little bit more. So LDA, can you see? So it's the square that I didn't cover because I don't think he's going to cover. But
that's not important then.
yeah,
That's not important. I was just wondering, we're not gonna face that in the midterm, right?
I hope not.
Oh, me too, I hope not too. We can move on, we don't need to go over it then.
I will still talk about this. So in case you're interested.
Okay.
So it's you finally still need to learn that.
Yeah.
Yeah. So it's either between or like this week or maybe that. So it depends on what base you have. If you have a small base, your major product is going to be more substituted alkene. Otherwise, it's going to be the less substituted alkene. It's because if your base is large, it cannot go into the center carbon, then usually it will just grab the first hydrogen EC. And that hydrogen is usually on the side. So if you have less substituted alkenes, this one is only one substituted. It's called Hoffman product. It's also in your chapter 7. So go ahead and read that section if you're interested in it. So bulky base will have major products in Hoffman, and then small base is going to have major products in Zaitsev, and that one is usually more substituted. So this is your, if you have both hydrogen, good enough to eliminate, then you think about this. It's a pretty good question. I hope you won't make this in your midterm.
Me too.
Okay.